Alright, hello and welcome back. We are going to finish up the logic slides today and then start a new chapter of the book titled Proofs. So we're going to go even further than we went last time, okay? There's a whole chapter on that stuff. So let's continue and finish the logic slides. So I want to start with a question for you. Alright, so let's do this. It's very good practice to be able to translate English, an argument that somebody's making, to pure logic, all of our symbols that we've been talking about. And that will help you figure out, because then you can use all the rules we learned about, if it's valid, like if it's a good argument, right? We want to be able to translate English to logic by replacing each proposition we see, something that's true or false, with a variable. And once we get it down into that form, that is called the form, okay? The form of the argument. So let us do that for an example, all right? So let's give the form of the argument for the following one, okay? And then we'll use the rules of inference to prove that it's valid, okay? So maybe I'll give the form for you, and then I want you to prove that it's valid. And then I'll give you time to do that, okay? So that's not a question. This is the part that you do. All right, so here is the argument. I will buy a new car and a new house only if I get a job, okay? We're assuming that, because we're concluding something at the bottom here, right? There's a line. Assumptions, conclusion. Hypotheses, conclusion. So I'll buy a new car and a new house only if I get a job. I am not going to get a job, unfortunately. I will buy a new house. Therefore, I will not buy a new car, okay? So this doesn't have to be a valid argument. We just want to find its form first, and then we can see if it is correct or not. That lets us get rid of the English so that we can just look at the actual logic that underlies everything. So the first thing I want to do is give variables for each proposition, okay? So what are some things that are true and false in this English here? So I will buy a new car. That is something that is true or false, all right? So that, let's call that P. P is I will buy a new car. And this is how you break it down. I will buy a new car and a new house only if I get a job. So there's also the idea of I will buy a new house. So let's make that its own little predicate. I will buy a house, and then only if I get a job. I get a job is also a predicate, something that could be true or false. I get a job, let's call that R. Okay, see how that's working? I am not going to get a job, that's just not R, we already have that. And then I will buy a new house, all right, we already have that. That can be Q, okay? So do you see how? And then the conclusion, I will not buy a new car, would be the negation of P. See how everything can be represented in terms of P, Q, and R now. So that is how we find the form. Here's the form of that argument now. All right, so we've got these three hypotheses and this conclusion. And by the way, if you ever see if and only if, I said this once before in English, for some weird reason, only if is normal if-then implication, but the word if is backwards implication. I didn't come up with that. It still doesn't make too much sense to me, and I still have to look it up, but now we know. So we have an implication left to right in this one. So I will buy a new car and a new house only if I get a job. So there's the conjunction of these two, P and Q. I'll buy a new car and a new house only if I get a job, okay? Implies I get a job, okay? That's how you make that one. That's part of the form. Boop, boop. That's the first thing. And then I am not going to get a job. That is not R. That's the form of the second hypothesis. And then I will buy a new house. That is Q. We're asserting that Q is true. And then our conclusion is, therefore, I will not buy a new car, and that would be the negation of P. Okay? So that is how you create the form of an argument. Does that make sense? Now I want you to try using the rules of inference on this. Okay, so give that a try. Here's this page as well, if you want to scroll back to it. See if this is a valid argument. Okay? So let's see if you got it. Let me copy all this so I can put it on the next blank slide, because there's some work we got to do. Dun, dun, dun. All right, let's see if this is a valid argument. So what can we do here? We need to end up with not P, and the only way we can get a P is right there. That's the only place it's coming from in my hypotheses. So I somehow need to flip around, go from like R to that thing, something like that. And we've used modus tollens before. We have the negation of the conclusion. Maybe we can do that. That might be helpful. Let's see how far that gets us. Okay, so I have an implication and the negation of its conclusion. That is good old modus tollens. Let's see what we can get from there. All right, so by assumption, we have this. So that's where we start. P and Q implies R. That's by assumption. And then we also have not R, the negation of that conclusion by assumption. It's a hypothesis. And now we can use these two to create the negation of the hypothesis. So now I have not P and Q for free based on modus tollens. And if I want to really show my work, it's modus tollens using 1 and 2. Okay? Those two hypotheses, those things that I know are true, because I'm assuming them to be true. So now I have this. I know that this is true. And now we can just use normal logic stuff to simplify this. Okay? So this is from De Morgan, right? De Morgan's rules. This is not P or not Q, if we remember that rule. And now, this is almost not P. I need to somehow get the not P out of not P or not Q. Okay, let's see how we can do that, maybe. Okay? Dun, dun, dun. So, do any of these look like I could use them to get the answer out? And if you stare long enough at these, and maybe you already did, you'll notice that this one looks kind of like what we have. We have an or, we have a negation of one of them, and then we must know that the other is true in that case, because it has to be true, right? We're assuming the or to be true. If we know one side is false, it must have meant that the other side was the true side. Okay, that's a disjunctive syllogism. Very long phrase, but we can use that. I know I have the negation of this, which is not Q, right? That's right here. That's just Q, because we can simplify two negations. So that's where I want to go with this. All right, so with this and Q, dun, 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 I can get at and apply the disjunctive syllogism rule. So let's get there, all right? So I need to have, I guess, the thing that I want on the left and its negation, all right? So let's do that. So it looks like I need this Q over on the left side. So let's make this not Q or not P. If you remember that, that is the commutativity of or. If we go way back up here, the commutative law for or, because apparently to use this rule, I need that thing on the left-hand side. You don't need to be this fancy when you're doing it in your homework, but I'm just making sure this is exactly the rule that we're applying here. All right, and this is the commutativity. I'll just say commute of or, and then I have Q as a hypothesis, but I need the negation of this. I need not Q. All right, so Q I have as a hypothesis, or an assumption, whatever you want to call it. I need to turn this into not Q, which is equivalent, right? By a double negation rule. If I could only spell double. So that gets me this. I know that this is true now. And so now I can use this and this by disjunctive syllogism. I have the left-hand side thing negated, so I know, therefore, that this is true. Okay? It matches exactly, and I want you to double check, it matches exactly this rule, okay? With the required things, the names changed and everything. All right? So now finally, I have not P by disjunctive syllogism. Yay. Where the P in the rule up here is not Q, okay? I'll do this in a different color maybe. because this gets weird looking. The P in that rule is not Q, and the Q in that rule is not P, right? Whee. So that's how I'm using it there. I have that. And then I have the negation of the left-hand side. The negation, not Q. Okay? And that's how I got it. So that was from, I don't know, I'll just name these, this can be 3, this can be 4. So disjunctive syllogism 3 and 4. Whee. And that's how I proved that not P is true. So this was a valid argument. Do you see how that's working? Hopefully the example helps if you didn't get it. Okay? But this is a proof. We found the form of the argument, and then we proved that it was valid. Assuming these things are true, we were able to conclude successfully, using rules of logic and inference, that not P was true. All right? Let's keep on trucking, because there's one thing that I didn't show you in this table, which was how to prove things involving quantifiers. So when you want to prove a quantified statement, the trick is to get rid of all the quantifiers, actually. So kind of like I was hinting at. But you definitely have to go in that order that I was talking about before. That will become apparent as I get to the inference rules. The trick is you replace the quantified variables with either with random elements, either an arbitrary element or a particular element that you get to pick. Okay? When it's arbitrary, it can't be special. It just has to work equally well, any possible element. And I'll get into what that means. This is how you prove a for all, because you don't assume anything about that arbitrary element, so it could have been any of them. So for all, it's true. And then if it's a particular element, it can be whatever you want. Just find one good one. That's, of course, how you prove that there exists. Okay? There's also the idea of proving versus using. Like things are in hypotheses versus things are in conclusions. You might have a quantified statement in your hypothesis, which you can use. That's different from having a quantified statement in your conclusion, which you must prove. Okay? So let me show you the difference there. Proving versus using. This is going to be a lot of text. Don't worry, I'm getting to an example. I just have to say it first. All right? So, let's see here. The difference between proving versus using is, of course, you know that a hypothesis is true already. You get to assume that it's true. So there's some special things you can glean from that. And it's your job to show that a conclusion is true. Like, you don't know it yet. Okay? That's the main difference. So if you want to prove for all x p of x, the trick is to pick out an arbitrary element of P's domain, call it A, and prove that P of A is true. The idea is, because the element was arbitrary, you knew nothing about it, then A could have stood in for anybody. Therefore, it's true for everyone. Okay? Don't worry if you didn't catch that. I'll give you more examples. If you want to prove that there exists, you have to pick out one good element. That's all. Find a B, such that P of B is true. It could be arbitrary or particular. Usually it's particular. You just got to find one good one, and then, because you found it, it's like, oh yeah, there is somebody for which P is true. I found it. It's called B. Okay? So that's proving. To use, when you have these things in your hypotheses, look what you know. If I know that for all of x, P of x is true, then I can pick out any element of my domain, like A, B, C, because I know it's true for all of them. That's what this means, right? We assume P of x is true for all x, so we can take anybody from our domain and conclude that P of that thing is true. Awesome, huh? That's very powerful. That means it's harder usually to prove it for all. To use that there exists, you just know that there is some element in your domain for which P is true. You're not really sure which one it is either. You just know that there's somebody, call it B or something, and you know that P of B is true. Okay? That's the best you can do, unfortunately. You don't have much information when you know that this is true, sadly. The best you can do is give that thing a name, call it B, and now you have P of B to work with and to use your other inference rules with. You got rid of the quantifier, but at what cost, I guess. All right, so this is usually not a very interesting use, okay? The others are very important, though. So let's translate all this to rules, which might make slightly more sense, and then we'll get into an example, which will make it fully make sense, I hope. Okay? So here is using, proving. Using, proving. These are for all. These are for there exists, and let's talk about them. So if you want to use a for all, you got it in your hypothesis, then you know that P of whatever element of your domain is, you can pick out C, whatever you want, you know that P of C is true. Okay, that's how you use a for all. You can get rid of the for all, kind of. Now you're working with P's. To prove a for all, when it's in your conclusion, you have to first take an arbitrary element, assume you have one, and then prove P of C for that arbitrary element, that you're not assuming anything special about it. That's how you know, because it was arbitrary, it's true for anybody. Anybody could have stood in for that C. Okay? And now let's do the there exists. If you know in the hypothesis, and you want to use the fact that there exists an X such that P of X is true, you know that there is some element of your domain, call it C, where P of C is true. That's what you can conclude. Okay? You have to be very careful here, and I note it down here. When you introduce this new name C, it cannot be anything else that you've ever seen before. Like if you have a C equals 42 up here, you cannot use and introduce a new variable called C again, because now you know it's not the case that it's equal to 42. That's not something that you can successfully conclude. That would be illogical. Okay, so if you're already using C, it's got to be now. You got to introduce a variable called D in that case. Okay, so this better be, it's called a fresh variable, something that you haven't used before. Okay, so just keep that in mind, otherwise it'll ruin things. And then this is probably the least common one to use, I would say, the least common rule of inference. To prove that there exists, if you want that in your conclusion, then you just need to find one good element, call it C, and prove that P is true for that C. Because there exists just means that there is somebody for which P is true. I found one. It's C. Okay? That's the idea. And remember that you need a new name when you're introducing new variables. Okay? That will be important later. So here's my example that I hope will make it all make sense. It's going to combine everything that we've been talking about. All right? So here is my argument. Assume these two things, prove this one thing. So notice that we have to prove a for all. We better, therefore, be using this rule eventually. Well, let's just start with that. All right? Let's pick out an arbitrary element in the domain for P, and let's make sure that we can prove the right thing. All right, let's pick out a random element, because we're eventually going to prove P of C for that element. All right, so let C be an arbitrary element. That's how you do it. Arbitrary element of P's domain. All right, and why am I doing this? It's part of, I'm going to name the rules. It's part of universal generalization. I got to pick out a random element, prove that P is true for that element. In our case, it's going to be, just P is true for that element. And then I can conclude that it's true for everybody. Okay? So this is part of, not the whole thing, part of, for all generalization. Okay? So that is the first step, because we know eventually we're going to need to use that. All right, so let's do that. And now it's our job to find. So our goal right now, the goal is prove P of C. Once we've proven P of C, then we have this, we have this. We can conclude our conclusion. So right now we need to find a way to get P of C out of the deal. Okay, let's do that. So I have two hypotheses right now. I know that for all x, Q of x is true, or P of x is true, and I know for all x, not Q of x is true. Do I have an element to which I can apply these for alls and get rid of the for alls? Oh man, I can use them, because they're in my hypotheses. I have an element. Oh man, I have a for all. Let's apply the for all. It's kind of like a function. Because I know it's true for every x. It's true for C. All right, let's do that. I know that Q of C is true, based on, I have C, let's plug it in here. I know that Q of C is true, or P of C is true, okay? And this is from me using this hypothesis and this, all right? That is universal generalization. Oh, sorry, I'm sorry. It is universal instantiation. I'm instantiating. All right, so that is for all instantiation. Yay. And so I know this. Let's also use the same thing, universal instantiation, for this one on C, because we have a C now. So I have this, and I have not Q of C. That's, again, universal instantiation. I'm going to try my best to copy and paste this, because that was a very long word to write. Whee! Stray thing, be gone. All right, so now I have these things, and these are easier to work with. Then I can use my normal logical rules with them, because these are just true or false values at this point. All right, so let's somehow pick out, because a goal is still P of C. We need to prove P of C right now. We can use this and this to prove P of C, can't we? Because I have not this and this or that. So where's the rule that can prove that? Dun, dun, dun. It is disjunctive syllogism. I have an or. I have the negation of the left-hand side. I can therefore know that the right-hand side must have been the one that was true. All right? So now I know that P of C is true because of disjunctive syllogism. That's an inference rule. And so now I have my goal. Now I can finally finish off my universal generalization rule. Because first I started with the top. Oops. Now I have this. So I can conclude what I wanted. I can conclude now for all x, P of x. Therefore, for all x, P of x, because of universal generalization. Using this and this. So with 1 and 2. Isn't that fun? So we just proved it for all. Definitely stare at this example for a while. This is a good one, I think. All right, so that's our first example, and now I want you to try. All right? So let me get the form for you again, and then I want you to try to use rules of inference to prove that the form is valid. All right, so let's prove this. So let's see here. Here's our argument. Let's find the form. We got to define predicates now. Express the hypotheses and the conclusion using those predicates. And then let's use rules of inference to prove that the form is valid. So the domain is the set of athletes on a team. That's useful to know. Here are our hypotheses. So assume this. Everyone practices hard or plays badly, or both. So normal inclusive or. Someone does not practice hard. Oh man, for all there exists. Prove that someone plays badly. There exists again. Okay? So here are the two predicates that I see. Somebody practices hard or they play badly. So let's say that P of x, let's define it to be P of x is x practices hard. And Q of x is x plays badly. All right? And again, the variables don't matter. So I could be like, let's define Q of y to be that y plays badly. No difference. All right? And so now let's use these to express the form of this. All right? So the form is, well, everyone practices hard or plays badly. So for all x, it's true that either, or possibly both, P of x or Q of x. Yeah? Just read that off. Someone does not practice hard, so there exists somebody in x such that not P of x is true. And I want to conclude that someone plays badly. So there exists in x. Again, I can use a z variable. It doesn't matter. there exists an x. These are all different x's, right? Such that q of x is true. So there's the form, and now we want to prove it. All right, so let's do that. So let's take this, copy it, bring it over here, and get started. So what did I skip? So there's it. And let's use our rules, right? So this is what we want. This is what we're trying to prove. Let us do this. So what does it mean to make a there exists? There exists an x such that q of x is true. I have to find just one good one, all right? So I need some element of the domain eventually, all right? So, and remember that the domain is the set of athletes on the team, so everybody on the team. And I want to use, eventually, existential generalization. So I need to find an element. Let's just assume that we have some arbitrary element, right? I don't know anybody's name, so let's just say, let's pick a player, call them C, all right? That's the first step of existential generalization. We know we have to use that eventually, so let's use it now. So let's say, let C be an athlete on the team. And, all right, that's part of existential instantiation. All right, and then what are we going to do with that C, right? We have a for all, so we can apply that to get out that P of C or Q of C. That might be useful. Let's do that. That might be useful very much. Is that a good idea to start? Because eventually we need to use this there exists as well, and to use a there exists, we also have to pick out some random element of the team. C is a particular element and P of C. So maybe let's actually do that one first. Let's get rid of the there exists so that we can get the not P of somebody. All right, there's somebody on the team who doesn't practice hard. Let's be able to talk about that person. All right, so let's let C be an athlete, and this actually is, I was thinking the right thing, but not saying it right. This is indeed existential instantiation. I'm using the there exists, and so I can prove that this is true, and I know that the conclusion is true here. All right, so not P of that C. So there's somebody on the team, call them C, that they don't practice hard, right? And so these two, they are both existential instantiation. That's what I get for free. And then, what can I do now? Dun, dun, dun. So I still have the C. I know that they don't practice hard, whoever that C is. I can also use the for all now on that C. Okay? I can get that particular person, either P of C or Q of C is true. All right? P of C or Q of C. I can conclude that using the for all. Right? I can use universal instantiation on that C. So it's just a bunch of pattern finding, this kind of stuff. Okay? Now, I need to somehow figure out that maybe Q of C is true, right? Because that would be my one thing for which Q is true. I found somebody. I think that's the best I can hope for. Can I use these two maybe to prove Q of C? Is that how you did it? So yeah, I think that's another disjunctive syllogism. I've got the thing, it's negation, so obviously it was that side that was true. Yeah? So Q of C must be true. That is disjunctive syllogism. All right. And then finally, that's all I needed. I had an element. I proved that Q is true for that element, and so I found somebody for which that predicate was true. That's existential generalization. Oh man, oh man. So I know there exists an x such that Q of x is true, in particular, that was the C we found, and that is existential generalization using, let's call it, I don't know, 1 and 2 again. Okay? And so that was our conclusion. That should be, I guess, a therefore, right? That's what we wanted to show. That is our proof. Do you see how we're using those quantifiers? And also proving those quantifiers. Does that make enough sense? So this is definitely something that takes practice, and so that's why I'll be releasing a new homework with this kind of stuff once we get into the proof slides as well. All right, so that is the first part of the lecture. Let me pull up now the next slides, and I'll be right back. All right, welcome back. Now we're going to talk about proofs, which is kind of taking what we did just now, all these things, which were kind of like following all these little rules. We're going to turn that into more English now that we know the rules. Okay, that's the job of writing a real proof now. Okay, so let's prove all the things, guys. Are you ready? So I guess the first thing that I want to do is maybe trick you into liking math if you didn't before, because this is technically a math class, right? Proofs are the beginning of what is known as higher math, people like to say, if you've heard that term before. It's very different to not higher math. I don't know, lower math, I don't know how you call it, but yeah, I want to tell you that math has nothing to do with plugging in numbers and computing values, which is maybe what you have known math to be your whole life, even up into calculus, right? Once you go farther than that, it gets cooler, I want to say. Modern math, calculus was invented way back when, right? Hundreds of years ago. Modern math is beautiful, in my opinion, and it can be really abstract, like we've been getting into. Right? Has nothing to do with numbers even. Has nothing to do with true or false even, kind of. So yeah, you'll notice once you take higher level computer science classes, you'll notice that we use this kind of math a lot. And so that's why we're giving you this class and forcing you to take it. Okay? So as a computer scientist, you actually have a special take on this stuff. You'll notice that, and I'll try and show you, that proofs, when you write them, they're really just like programming. All right? And it's really an art form to write a good proof. I'll show you some really cool stuff in these slides. I'm very excited to teach you how to write a proof, okay? I think it's magical to learn some of this stuff. So, yeah, this is my rant saying that I would probably have been a math major if I knew ahead of time, but it is what it is. I'm just happy to teach this class, okay? So, hopefully, I can trick you into liking math as much as I do with these slides. We had to get here. We had to do some very low-level stuff in the logic slides to be able to we had to walk in order to run here. Okay, that's the idea. Okay, so let me define a bunch of stuff that we're going to use later. We'll just come back to this slide. All right. So an integer, a whole number, right, is even if there is some other integer k such that x equals 2k. Okay, we're going to convert this all to logic. This is English. Let's convert it to logic. So an integer is even if there's an integer k such that x equals 2k. So there exists a k such that x equals 2k. That's what it means to be even. A number is odd. Integer is odd if it's equal to 2k plus 1. There's an integer k such that x equals 2k plus 1. That's the difference between even and odd. That's the low-level definition of it. Okay? And we can prove that a number is even or odd. We have to use that definition when we do. Okay? A number is rational if there are integers x and y, such that that y is not 0, because you don't want to divide by 0, and r equals x over y. That's what makes a fraction, a rational number, right? So there exists an x, there exists a y, such that y is not equal to 0, and r equals x over y. That's what it means to be a rational number, a ratio of things. An integer x divides an integer y if and only if, so biconditional, x is not equal to 0 and y equals kx, right? So there is something it was able to divide into, x was able to divide into y. It's some multiple, right? That's the idea. And k is how much you got to multiply x to get y, okay? So let me show you that. And we write x and then not a slash. It's not slanting. It's just like the pipe symbol. X pipe y, I guess. X line y to mean that x divides y. So that's how I'll pronounce it. X divides y. Okay? That is the idea there. So x divides y if and only if. So biconditional. 2 arrows going each way. If and only if x is not equal to 0. Dun, dun, dun. And y equals kx for some integer k. So there exists a k such that y is equal to kx. Okay? That's what it means for x to divide y. So if x divides y, then y is said to be a multiple of x, because you can multiply x by something to get y. Y is a multiple of x, and then x is either, like we say, it's a factor of y, or it's a divisor of y. We'll get into that, okay? So we just write this, though. We say that x divides y. That means that y is a multiple of x, okay? So we'll see that used later. And then we have primes. That's useful too, right? A number is prime if and only if it's greater than 1. And for every positive integer, if m divides that number, for every positive integer, call it m, if that number divides n, then it must have either been 1 or the number itself, right? That's what it means to be prime. There's only 2 possible divisors. We have 1 or that number, nobody else, right? So n is prime. I'll write it like that. N prime, if and only if n is greater than 1, and for all positive integers m, for all m, this is how you write m is positive. If it's positive, m is greater than 0, implies that, this is a very ugly definition, I'm sorry. Let's see, I might need more room actually. Let me rewrite all of this. So n is prime if and only if n is greater than 1, and I'll just start writing more on this side. I guess I'll write it down here. And for all m better be positive. For all m, I don't know, such that m is greater than 0, if it's greater than 0, we say. I'll just write it and explain it later. M is greater than 0 implies, that's how you know it's positive, that if m divides n, then, if you know that, then, it's another implication within an implication, then m is equal to 1, or m is equal to n. This is how you can formalize this stuff in math. We're not going to use this too much, but now you know that's how you can formalize it, at least. Crazy looking. So that's prime, and then an integer n is composite if and only if n is greater than 1, and there is an integer m such that it's between m and 1 and n, and m divides n. So you could negate this, I guess it's equivalent, or you could just write it out here. Right? So n is composite if and only if, I'll use single arrow this time, n is greater than 1, and there exists some integer m such that 1 is less than m is less than n, and m divides n. Right? So that's looking pretty ugly. But that is, like, this would be how you prove it, right? You'll use our rules of inference to prove these things. If you want to know that a number is composite, this is what you have to show. If you want to know that a number is prime, this is what you have to show. Crazy, huh? So we'll be working with the simpler definitions for my examples, but this is how you can translate stuff to full-blown, hardcore logic where you can prove things in. All right? So here's an example for you. Please try to use those definitions on the previous slide to say whether n, which is equal to 42, whether that number n, which is 42, is even or odd. So tell me if 42 is even or odd, please. And if it's even, you better show it to me. Show that n equals 2k for some integer k, because that's how you have to prove that it's even. Right? If it's odd, show that it equals 2k plus 1 for some integer k. What does it mean to prove for some, right? There exists. You got to find that thing. You got to do math, okay? So pause it, try to write it out. But this is like our simplest English proof, all right? So n equals 42. It's of course even, right? Because n equals 2 times 21. And so if you just take k in the definition to be 21, then n equals 2 times k, and n is 42. So I just implicitly used a there exists. I implicitly proved a there exists. Do you see that? That is the level at which I want to get you, all right? So we know the fancy definitions of how to prove a there exists, but we also want to know how to prove it in English because I can follow your logic, okay? Isn't that nice? So that's the first example for you. Now I want you to try this one. This is something different. It's not these definitions anymore, but I want you to think about this. All right, so write the following without the negation. Both of these. All right? What does it mean for it not to be true that x is greater than 42? Okay? What does that mean? So here is what it means for x to be strictly greater than 42. Here's the number line, right? Here is the number 42. And so for it to be strictly greater than, it's not including this one, but all of these. That's what it means to be greater than 42. And I want to negate this, right? So if I want to negate that, that means I want everybody that's not included right now. So it's 42 and less, all right? So this becomes x is less than or equal to 42, right? So you flip it and add an equals to. Does that make sense? Likewise, let's prove, or let's figure out what the opposite of this is. What does it mean for it to not be true that y is less than or equal to negative 100? All right, so let's find negative 100 on the number line, and it's inclusive this time. So here's negative 100, and so y is less than that, less than or equal to that, so it's that one, and everybody over here. That's what it means to be less than or equal to negative 100. So the opposite of that would be everybody that's strictly greater than, and not including, negative 100, right? So that becomes y is greater than, without an equals to, negative 100. You see how to do that now? So this is just something that you'll have to get used to when you're proving things. Just flip it, add an equals to. Flip it, add a, or get rid of the equals to. Okay? That's the opposite of those things. And so now we can do all of these. So you want to negate a less than, becomes greater than or equal to. You want to negate a greater than, becomes less than or equal to. This becomes strictly greater than, this becomes strictly less than. What does it mean for it to not be true that something is equal to something else, right? Well, that just means that it's equal to, right? Negation of x is, equal to 42. That just means that it's equivalent to, well, that just means x is not equal to 42, right? And the negation of, like, x is not equal to 42. If it's not true that it's not equal to 42, that's a double negation, right? That is, well, that must just mean that x was 42. Does that make sense to us? That's the idea. You could do it on a number line if you wanted to, like, all right, x is 42. Negate that. Well, it's everybody that's not it. Or x is not equal to 42, so it's everybody but 42. All of those, not including this one. So, therefore, the negation must have been just the 42. Cool, huh? All right, so it's not equal to. Hopefully that is logical enough. That will come up later. And then, yeah, this is the last thing that I want to talk about. We'll get into really, like, from this chapter's point of view, in English, proving a for all, proving a there exists, all that stuff. But let's get us ready, all right? So, more definitions, yay. We just have to say these words once so that we'll use them forever. A theorem, that's a new word. A theorem is a statement that you can prove to be true. So it's just something you want to prove, okay? It's a statement that has a proof and it is true, all right? So it's a theorem that the square root of 2 is irrational, for example. It's a theorem that 42 is equal to 41 plus 1. Okay, it's something that we can prove to be true. All right? If you want to prove a theorem, though, this is just the statement itself. To prove a theorem, you can use logic, so everything in the previous set of slides, all our fancy rules then. You can use any assumptions that you made in the proof statement, your hypotheses, for example. That brings us to another word called axioms. Those are just things that you assume to be true outside of the proof statement. There's some technicalities there. It's somewhat separate from a hypothesis. We won't really get into that, but at least you've heard the word now. You can use, of course, any previously proven statement / theorems because they've been proven true. It's something that you know is true, right? So those are like extra hypotheses. Once you prove a theorem, you can use it for the rest of your life. This lets you build up every single bit of math, little by little. You have a proof for everything, and you can use those mini proofs to build bigger proofs. Okay? It's like writing a program. These are little functions you're making a big function with, all right? And so, essentially, when you're writing a proof, this is how I want you to think about it. You're assuming, like at the end of the day, it's an implication, right? Assuming a bunch of stuff, and that leads to your conclusion, all right? You assume that your assumptions are all true, and all the previously proven theorems are true, because, I mean, you know how to get to them. You know that they are true, right? You've proven them before. So assuming all this wealth of knowledge, prove that your conclusion is true, and at that point you can leave it to logic. Use all the rules you know about, and that's how you prove your statements. So this chapter is more Englishy, and I'll get into that next time, but that is the start of it. All right, so I want to release your next homework. Boop. Right here, this will be homework 1 due week 4. It'll be about the proofs chapter. Okay, so keep that in mind. And then I also want to release your next lab, and so I will do that in the lab video. So I'll see you there.